So let's I'll go back to the initial image that I showed. So now we are going to deal with this particular step, right? How do you convert the clean text into numbers and representations that we could use, right? So yeah, let me just go back to that. Right. So as is already covered in the class, we can convert text into something called one hot encoding vectors. Basically, they are vectors like this, where each position is indicative of a particular word, and it is 1 if that word is present, it is 0 if it is not present, right? It is as simple as that. So let's say you have a very simple use case where you have only 3 sentences or 4 sentences in your corpora. First thing that you do is you clean them, you lowercase them, and you replace you drop the punctuations. Let's say that's what has happened here. And you are then creating the vocabulary. Vocabulary is basically a collection of unique words in your whole corpus. And then so vocab here is basically a dictionary where each token is given one key, and the value is basically just the ID or the numerical ID of that particular token, right? You can and this vocabulary is important before you go and create a one hot vector, right? So let's say you take the sentence man bites dog, and you can convert into a representation like this, right? So here you from your vocabulary, you know that there are only 6 tokens in your whole vocabulary. So for representing any sentence, you would need a vector that is of dimension 6, right? So you can see that each word is represented by a vector, right? And it is one hot encoded because only that position in the vector is one for which the token is present, right? So man is in the 3rd position. The token man is on the 3rd position. So 0 1 0 1 2 or 1 2 3, whichever indexing you follow, you know that this is 1 here, all the other positions are 0, right? This is why it's called one hot encode. So and you can basically flatten them out. So there are 3 words in your token, so you ended up with a matrix of 3 cross 6, right? Each token is represented by a vector of dimension 6. There are 3 tokens, so you end up with a matrix of dimension 3 cross 6, right? Should be fairly simple. Now, but you want one vector for one sentence, right? So you can just flatten them out. So basically you can flatten a 3 cross 6 matrix into a 6-dimensional vector just by adding them up, right? So that is what is happening here, and you can see that 1 0 1 0 0 0, right? All right. So the word here was man and dog are good, right? But you can see that only 2 positions are high on what happened to the word good, right? Again, you go back and see that these words are not there in your vocabulary at all, right? So there is no position to indicate them, hence they do not occur, right? So you need to be very careful while creating this vocabulary. It needs to take into account all the words that are there in your corpus, right? And if tomorrow you come up with you come across a sentence which has words which are not in your corpus, in that case you would end up with not representing that in your vector, right? So and this is bound to happen. This is a very common occurrence where you come across an unknown token that was not seen in your earlier corpus, right? So there are design choices that you can make. You can either drop it, or you can keep one position, and you will one position for all the unknown tokens. No matter which unknown token comes tomorrow, if I come across unknown token, I'll keep that position as 1 and everything else is 0. So this is what one hot encoding is, and this is how you would code if you were to write on its own, right? So this is just to show how do you implement it ground up. But there are again inbuilt libraries or libraries that you can install that do most of this stuff, most of this heavy lifting, code heavy lifting for you, right? So Scikit-learn is a library that offers a lot of these functionalities, not just these feature extraction methods, but also it offers a lot of functionalities like models, exposes a lot of models that you could use, right? And here on we'll use Scikit-learn as a library much more often, and it's not peculiar or specific to NLP. It is used across in most of the machine learning applications, right? So it offers two things. So we are looking at two functions here. One is label encoder and one hot encoder. And yeah, label encoder is basically giving you an ID to each of the unique tokens in your corpus, right? So it takes values as the input. Values is basically nothing but the list of tokens, right? And label encoder is just making sure just counting the words, right? It assigns each word a particular ID, and you can see that it also keeps track of which token has occurred how many times, right? So the positions here are indicative of one word, right? So the word one is basically indicative of I think dog here, and 4 will be indicative of man and stuff like that, right? But either which way, I think specifics apart, what is happening here is that there is an ID associated with each token, right? And if you were to convert this into a one hot encoded matrix, you can use a inbuilt function called one hot encoder, and it creates a vector representation, one hot vector representations for you, right? Quite simple. So what you were doing above was writing a lot of pieces of code, counting the vocabulary, and then writing a function to create a one hot vector. Your life is made easy by using Scikit-learn and this particular function. All right. So a related concept is a bag of word concept. Bag of word concept is where you are dealing with you're counting which word has occurred how many times, right? So you know that dog has occurred 10 times or man has occurred 5 times, stuff like that, right? So you represent a sentence as a bag of words, like, and this is the vector representation, right? So just to go back, so this would be the bag of word representation for the word, this particular sentence, right? So you had one hot encoded vector for each position and for each token, and you had summed it up or flattened it up into one vector representation of the sentence, right? And this could be thought of as the bag of word representation. Right. Again, for doing this, you use a functionality called count vectorizer that is present in Scikit-learn feature extraction text submodule, and you can give your own corpus, cleaned corpus, and it will be capable of creating representations like this, right? So you can see that a sentence is broken down into its bag of words representation. There are two things you can do here. You can let's say if the word dog has occurred two times in a sentence, right? A particular token has occurred 2 times in a sentence. You can either keep the count, or you can just keep a binary value, just 1 or 0. 1 or 0, the binary approach will say that dog had occurred or not, right? In that sentence. But you can also go the other way around, where you say, instead of keeping the binary values, I want to keep count, how many times that particular token occurred, right? So that could be controlled by this, right? So for count vectorizer, if you give this argument true, it will keep the binary values. If not, it will keep the counts, the number of times it had occurred. Again, in the previous section we had seen that instead of looking at individual tokens, you could also look up combination of tokens with bigrams and trigrams, right? So if you were to you can use that also as a feature in your bag of words representation, right? Instead of looking at how many times a particular token had occurred, you can also look at how many times a combination of 2 words, that is a bigram, has occurred, or how many times a trigram has occurred. Count vectorizer, if you give an argument saying that I want to keep all the unique n-grams from the range of 1 to 3, that means that is equivalent to saying I want to keep n-grams, I want to keep bigrams, and I want to keep trigrams, right? So in such case, you can see that we can using the same function, you can achieve that, right? But I want to also bring your focus to the size of this vector, right? So you have a vector of this size when you were just looking at tokens, just unigrams. But as soon as you went to bigrams and trigrams, you can see that the dimension of your vector increased, right? Which is logical, right? If you are looking at bigrams and trigrams, you can see that there will be many more combinations, and for each of those combinations, you would have to allocate space in your vector, right? So while bigrams and trigrams would be very useful in encapsulating the information within the sentence, the overhead here is that your vector becomes too large, right? And it has implication in terms of the memory it occupies. It has implication in terms of how well or how correctly or incorrectly the models would be able to work. Right? A similar associated concept is TF-IDF. So instead of just keeping a count of how many times this token has occurred, we can also encapsulate the notion of how many is this token relevant only for me, only relevant for this document, or it occurs all across document, right? So simple notion to understand this is, let's say, the stop words like and, the, a. These would occur across all the documents, right? So if you are asking the question, is this token relevant or important in this doc, or does it invariably occur across all the docs? Word counts will not be able to tell you that information. Word counts will simply tell that this word has occurred here these many times, here these many times, and here these many times. But if you want to capture this, whether this has occurred here, okay, but has it occurred only here, or has it occurred in other documents as well? That's where TF-IDF comes into play, right? So TF-IDF has 2 components. One is term frequency and one is inverse document frequency, right? So let's look at an example that would make things much more clear. You have 2 documents, you have tokens and their relevant counts, right? You can see that the token this has occurred across both the documents, right? So if you were to just calculate the term frequency is how many times that word occurred divided by the total number of tokens in that document. So it will be 1.5, and it would be something similarly calculated for document 2 as well, right? But you can also see that it has occurred in both the documents, right? So this is probably like a stop word, and it occurs across most of the documents. So stop word is just an example. There could be other cases why this happens, why a particular token occurs across all the documents, right? So that is captured by inverse term frequency, right? So the formula is this. Without going into the details of it, what it will do is that if a token is occurring across all the documents, it will give you a value 0, right? So when you combine TF and IDF, which is basically a multiplication of these 2 terms, you will end up with 0, right? Now look at a token like example. Example occurs here thrice, but does not occur in document 1 at all, right? So in such a case, what happens is that TF because the token example doesn't occur in D1, it will be 0. It occurs in D2, so the TF for that would be a bit higher. But look at IDF. IDF is not 0 here, right? Because it is special to this document. It is not a common term that is occurring across all your documents, right? So in such a case, you will get a non-zero IEDF, right? So if you multiply here, you can see that the token example, the value it has is a non-zero value, right? Whereas the value of this, which is occurring across all the documents, was 0, right? So it is basically a weighing or enhancing the tokens that are special to a particular doc, right? So while in one-hot encoding and in bag of words representation, you were looking at either binary values, 1, 0, or the counts. In TF-IDF, you end up with these floats, right? Where it could be 0, it could take multiple values across the range, right? And this could again be very simply implemented using the TF-IDF vectorizer. You can see that it is not always 0 or 1 or a count. It is a much more it's a float, and it captures a lot more information that bag of words is not able to, right? And it has been shown that these words work, these approaches like TF-IDF work a bit more better than simple word count or bag of words based. Right. So this is the feature extractions method that we have seen so far, one hot, bag of words or TF-IDF. These are all count based, right? And count based, while they are good for certain applications, they have certain limitation as well. One limitation that we already saw is that if you're looking at bigrams and trigrams, your vector could be arbitrarily large. It could blow up very quickly. This is a very simple example where we are probably dealing with 6 tokens, but in your large corporas, you will end up with you're likely to deal with millions and millions of tokens. So, computationally, it's a problem, and it's also it's not a guarantee that in such a large matrices which are sparse, like many of these matrices will have zeros, right? It's because you have one sentence which is 10 tokens, but you have a million tokens in your vocabulary, right? So you end up with a vector of 1 cross million, but many of those positions will be 0 because those only 10 tokens are there in a sentence, so many of those other tokens positions will be zeros. That this sparsity is also an issue. Sparsity, by sparsity we mean that many of the positions in the vector or in the matrices are zeros, right? So that if they are zeros, that essentially means that you're occupying a lot of memory and not a lot of information is present in that. So is there a way to condense this? Is there a way to boil this down into smaller matrices and which are capturing a bit more information, right? So this is where dense representations came into picture, word vectors. So instead of word counts, bag of words or bag of word counts, can we create representations which are smaller and are able to capture semantics, right? So in representations like this, you are not able to capture whether you are not attempting to capture the meaning of the words, right? So this is where word to word embeddings became very popular a few years back. So broadly speaking, what word vectors do is that they are given the adjacent words, they try to predict the central word, right? So in this method called CBOW, continuous bag of words, I have I'm a particular token at this position. I'm taking 2 words from here and 2 words from here, and I'm trying to predict this central word, right? That is the game I'll play. That is the way I'll train my network. And this is the other way around. I have the central word. I am to predict 2 words here and the next 2 words here, right? So using this method, using this as a training procedure, you have a large corpora and you train your model like this, right? You keep training for each of the words that you keep seeing, and you end up with word vectors. That's a very large, this is a very bird's eye view and bird's eye explanation of word vectors. But for now, I think this is sufficient to move forward. So as I said, one is that they are reducing the sparsity. If you had a million words in your vocabulary, now you do not really need a lot of for representing each word you don't, or each sentence you don't need a vector that is million large. So here you can control whether you want to represent it with a 10-dimensional vector or 100 or a 300 or a 400, right? So you have a control here, and it's a thing that you can configure, right? There is no correct dimension here. It could be 50, it could be 100, it could be 300, and these have varied across models. So the reason why these became very famous is because you could do arithmetics like this, right? You have a word vector for king, and you have a word vector for man, you have a word vector for queen, and you have a word vector for woman, right? So if I were to ask a simple question saying that king minus man plus woman, right? So you have a word king, you're subtracting the word minus, you are subtracting the word man from it, and you're adding the word woman to it, right? Intuitively, you could say that this should lead to a word like woman, right? From the notion, from the entity called man, so from the entity called king, you had removed the entity called man, and you have added an entity called woman, right? So that essentially makes it a queen, right? So and if you do this using word vectors, these arithmetic functions using these word vectors, they make they work, right? Surprisingly, they work well. Which was probably not the case if you were looking at bag of word representations, right? Now let's look at how this is even possible. Just a second. Yeah. So you have a lot of words which are represented in your vector space, right? Vector space is nothing but you think of it. Let's say a 2D vector space is basically a plot like this, and x and y dimension, two-dimensional plot, and each word could be represented at a particular position, right? So how these are trained? Let's say, how do I know when the word father is located in this position, right? So these are learned. These representations are learned by playing or by training a network like this, right? So here what's happening is that there's this notion in NLP called distributed semantics, right? That is where the theory of this is coming from. And there's a very famous saying by a researcher named Firth, saying a word is known by the company it keeps, right? So if I'm capable of guessing what are the adjacent words given a word, if I'm able to predict the adjacent words, or given the adjacent words, if I'm able to predict the central word, that means that if I'm very good at doing this, if I'm getting good at predicting this, that means that I'm learning something about the words, right? That's the intuition here. And by training these two methods, this is essentially the game you're playing, right? You have these, and you are predicting this, or you have this and you are trying to predict the adjacent words, right? So input word, target word, input word, target word. And this is the training methodology. I will leave it up to you to go through this particular image and understand it. But once you train your model over a corpus, you will end up with word vectors, right? And researchers who have trained word vectors on really large corpus, they have released it for other researchers to use, right? So if I have trained this over the whole Wikipedia corpus, or over the whole Google News corpus, the resulting word vectors could be used for any application, right? So that's the intuition here. In this training procedure, I am not there is no task specific thing, right? You are doing a very generic task of predicting the surrounding words or predicting the central word. So this is just pre-training, right? So there is no task specific component here. So you can use this word vectors that you train, and you can use it for task specific thing, right? Let's say you can take the word vectors trained here and use it to, let's say, sentence classification, like sentiment analysis, or you can do simple stuff like let's say even the POS tagging or the NER tagging, named entities tagging that we saw a bit earlier. Even these models could be used there. This pre-trained embeddings could be used there. So here we are basically downloading a pre-trained vector called glove. So it's a variation of this method. There's a lot of technical detail there. I'm not going into that, but it is essentially glove vectors are learned in a manner comparable to previous method. So and you can see that there are around 4 lakh tokens in this trained vector, right? So in that model's vocabulary, there are 4 lakh tokens, right? So there will be a so we can query for any word. Let's say if you want to query a vector for word India, it will return a vector, right? And the size of this vector usually varies from model to model, right? For glove, this is the dimension. For, let's say, a model like fast text, which is another model of similar nature, it would be a different dimension. For word to vec is another comparable model, it would have a very different dimension. You can train your own model, and this could be this dimension could be something that you can control for. You can try various combinations. But yeah. So you can get similarity, as I said, using these word embeddings, you can do very simple arithmetics, and you can get similarity between two words and stuff like that, right? So so you can get, let's say, similarity between Twitter and Facebook, Twitter and Samsung. You can see that Twitter is more similar to Facebook than Samsung, which intuitively makes sense also, because Twitter and Facebook are social network platforms, and Samsung is, let's say, an electronic manufacturer. And there are a few more demonstrative examples, but yeah. So here again, most similar, the function most similar can take two arguments. One is positive and negative. Positive are the words similar to it, and negative are the words, dissimilar to it. So by this syntax, what I'm saying is that I want words which are similar to Tokyo and India, but are dissimilar to Delhi, right? So that is what is being done here. And this could be any combination that you would want. And there are, like most similar, it also has few more functions like doesn't match or yeah. So all of this is done using a library called GenSim. GenSim is a library that you could use to read pre-trained vectors, that could be used to train pre-trained vectors, and it could also be, once you have pre-trained vectors, you can also do very simple functions like most similar, or query for a vector, query for a word, stuff like that. So in here I have few more cases of how you can train such word embeddings. You can load a corpus and you can just using this model, you can just train it, right? This is the syntax, right? Right. So in the next part, the last part of this tutorial, what we will do is that we'll look at how we can use these representations, bag of words, TF-IDF, or even the word-to-vec representation, and let's say do a simple classification task. So we have already looked at feature extraction methods like count vectorizer and bag of word count vectorizer and word-to-vec, and we can now feed those representations into models that are there in Scikit-learn, like multinomial, naive Bayes, or logistic regression, or SVC. And there could be other combinations as well. This is just for demonstrated. And we can look at how do I compare performance across models. So what follows here is basically, we take a toy data set. This is a data set where each economic news article is basically tagged for few values, right? Whether it is relevant for US or not, and values like that, right? So this data has a feature called relevance, whether that is relevance for US or not. Let's say if this was a sentiment analysis task, this feature, this column would be sentiment, and there will again be no, yes, not sure. So and this is the data set that you have. You have 82% of your samples are not relevant, 17% are relevant, and we were not sure about, let's say, 0.1% of that data. So in these cells, what we have is some pre-processing. You can clean the data, and you can drop the stop words and all that. And then you are basically, before you train a model, you always split it into train and test, right? I'm sure you are already aware of it. Without going into a lot of detail, let's skip to the next one. Once you have split the data, then you can create your representations. So we are using bag of word representation here, using the count vectorizer, something that we have already seen, right? And using that, we create a vector for training your data that becomes your xtrain, and you also do the same for your test, right? So train set would be used for training, and test would be where you will be generating the performance measures. So here you have picked a model like multinomial naive Bayes, and you have just train a model, right? So the nb.fit, this is the syntax used for training a model. And for prediction, it is more or less the same. Once you have trained a model, to that model you are feeding the text representation of test set, right? So using that, you can make the predictions. Once you have predicted, you can boil it down to accuracy or confusion metrics, and you can assess whether your model is any good or not, right? So again, most of these functions are basically functions that are there, inbuilt functions that are there in sklearn library, but let me spend a minute on how to interpret them. So accuracy, you are well aware, it's basically how many of those predictions did I make correctly, but that measure accuracy does not capture the whole picture. You would also want to look at a confusion matrix like this, right? So here you had two classes, right? Here you were you dropped the not sure classes earlier, and you have only two classes, relevant or not relevant, right? So this diagonal is what is the correct is the predictions that you made correctly. These are the ones that you made incorrectly, right? So what it is saying here is that 42% of the relevant ones were classified correctly, and 58% of those ones were classified as not correctly, as relevant, right? So yeah, so true label and predicted label, and you can use this to interpret a bit deeper into your results. So what follows after this is a few more variations where you can limit the number of features that are there in your model, in your bag of words representation, and you can basically do the same analysis again. You can see that the performance changes a bit. But yeah, so I think here is where we can play around with different models. Like earlier we were doing different ways of creating vector representation using count vectorizer or word to vec. Here I am just trying the same mod, using the same data, I am trying different models, right? So yeah, so I think this is the total summary of what we wanted to cover in this tutorial. So let's go back to where we started, right? So we started with, let's say, accessing raw text, reading raw text, normalizing them based on few stop words, special characters, and etc. Then we figured out how do we convert this into numbers, bag of word representation, one hot vectors or word to vec, and we looked at a very simple toy example of how we can use those representations to train a classifier, right? So this of course covers the whole pipeline, but it only covers the basics of these pipelines. Of course, at each of these steps there are multitudes of depths that you can go to, but I think this is a good starting point, and you can use this as a starting point and explore multiple ways you can represent the text, multiple models that work well, and multiple tasks that are done in NLP. So this is where we can stop with this tutorial. In case of any questions, I think you can reach out to us, and we'll be happy to help. Thank you.